So now this is a third important theorem. There is a theorem on gradient. Okay. So first we have studied a divergence theorem. In the divergence theorem, the region we have considered is a volume. Okay. And what is the boundary for any finite volume? It is a closed surface. So divergence theorem gives us a relation between volume and closed surface, a region and its boundaries. Okay. So when you observe the Stokes theorem, in the Stokes theorem, the region we considered is a surface, finite surface. What is the boundary for any finite surface? It is a closed path. So in the Stokes theorem, we give the relation between a surface and its boundary closed path. Okay. So that means in the divergence theorem and in the Stokes theorem, we take a region, we find a boundary for this region, and we give the relation between a region and its boundary. Okay. Same thing happens in the case of theorem on gradient also. We consider a region and we find the boundary. We give the relation between a region and its boundary. Okay. So first I will write the region. So here already in the divergence theorem, region considered is a volume. In the Stokes theorem, region considered is a surface. So in the theorem on gradient, region we are going to consider is any finite path. Any finite path. And what is its boundary? What is the boundary for any finite path? Okay. So just if you consider any finite path like this. So path starts at A and path ends at B. Okay. Then what are the boundaries for this finite path? Boundaries for this finite path are endpoints. Endpoints are the boundaries for this finite path. Okay. So I am going to write the same thing. Endpoints are the boundaries. Okay. So here same as that of divergence theorem and Stokes theorem, here in theorem on gradient also we have a relation between a region, finite path, and its boundary endpoints. Okay. So first I write finite path. Finite path is from A to B. Okay. Now in the divergence theorem we used divergence operation. In Stokes theorem we used curl operation. In theorem on gradient we use gradient operation. Okay. So differentiation here we use is gradient. Okay. So you know that gradient is applicable only on scalars, scalar fields. So it is a line integral, alright, dot dl bar. Okay. So right side equation must be in terms of its boundary. Boundary are nothing but endpoints. Okay. Here just for an idea, you can observe here, there is a differentiation here, there is a integration here. Okay. So integration and differentiation both are with the spatial coordinates. That is, they are with respect to x, y, z. Okay. You can cancel spatial differentiation with the spatial integration. Then you get only this parameter, the scalar at point B minus scalar at point A. Okay. So right side is in terms of its boundaries or in terms of its endpoints. Okay. So this is called as a theorem on gradient. Okay. So here by observation we say that all the three theorems, divergence theorem, Stokes theorem and theorem on gradient, all the three theorems gives the relation between a region and its boundaries, but with the help of a vector differentiation or if a spatial differentiation. Divergence theorem will use divergence operation, Stokes theorem will use curl operation, and theorem on gradient will use the gradient operation. Okay. So here if you write this one in the form of a formula, so you can observe here integral A to B gradient of, we need to consider any scalar field. I consider potential. Electric potential is a scalar field. So dot dl bar is equal to potential at point B minus potential at point A. This is the formula. Okay. So by observing this one, you can easily understand this is right side indicates a potential difference. Okay. So potential difference formula is given by this equation. Okay. So this is the theorem on gradient. As we have discussed, so divergence theorem, Stokes theorem both gives alternative methods to find the same quantity. Okay. Similarly, this theorem on gradient also gives an alternative methods to find the same quantity. Okay. For example, you consider any curve here. This is the curve. Okay. So here we would like to find what is the height of this curve. What is the height of this curve? Yeah. So to find the height of this curve, we have two ways. One is, let us find differential heights or small heights. Yeah. So we consider this is H1, H2, H3, like up to this one. Okay. So then if you want to find the total height of this curve, what do? You are going to perform addition or summation of these differential heights, okay, or small heights for all the values of I. Hence you are going to get total height of the curve. Height of the curve. Okay. That means in this method we used addition of differential heights to find the total height. Okay. This is the first method. There is another way. If you know start point and end point, or starting height and ending height of this curve, then how do you find this one? You are going to find ending height HB minus HA. This difference will also give you height. Okay. There are two methods to find the height. One is with the help of addition, another one is with the help of subtraction. There is end point height minus start point height. Same thing we have done here. Okay. This here integration is like a summation. So in the left side we find the total value with the help of summation or addition or integration. Okay. Same value can be found right side with a finite value of end value minus initial value. Final value minus initial value. Same as the right side here. Final value minus initial value. Okay. So like this, this theorem on gradient also gives an alternative methods to find the same quantity. Okay. So all the theorems we have studied, all the three theorems we have studied gives a relation between a region and its boundary. Okay. With the help of different spatial differentiations. Okay. And also all the three theorems gives alternative methods to find the same quantity. Each theorem gives two methods to find the same quantity. Okay. That is what we have studied. Okay. So here let me give the conclusion. You can take it as a note. So first theorem is divergence theorem. What is the region in the divergence theorem? Volume. Volume is the region. Okay. And in the divergence theorem, what is the differentiation we use? Name itself says the divergence theorem. So we use the divergence operation. On divergence is applicable on any vector into dv is equal to, what is the boundary for any finite volume? Boundary for any finite volume is a closed surface. Okay. Closed surface integral on the same vector a bar dot ds bar. This is the divergence theorem. Okay. In the Stokes theorem, what is the region we consider in the Stokes theorem? Surface. So Stokes theorem is also called as a theorem on curl. Okay. Or fundamental theorem on curl. So what is the operation differentiation we use here? Curl operation. Curl operation on any vector field a bar dot ds bar. So what is the boundary for any finite surface? Closed path. So closed path integral of a bar dot dl bar. Okay. Next, third one, theorem on gradient. In the theorem on gradient, what is the region we consider? We consider is a finite path. Finite path means we should have a starting point and also ending point. Okay. And what is the differentiation we use here? Gradient. Name itself, theorem name itself says that it is a theorem on gradient. We use the differentiation called as gradient. Okay. And gradient is applicable only on scalar functions like f. Okay. Dot dl bar is equal to, so what are the boundaries for any finite path? End points. Okay. So f at end point minus f at starting point, f of b minus f of a. Okay. So like this, all the three theorems are based on the relation between a region and its boundaries with the help of a vector differentiation, and all the three theorems gives alternative methods to find the same quantity. Okay. So these equations we are going to use directly in the electromagnetic fields, especially in the Maxwell's equations. Okay, so this is about vector integration or theorems in vector integration. Okay, so this is about vector integration or theorems. Okay.